right, thank you. Thanks. Thanks everyone for coming to my talk. So I'll be talking, or let me introduce myself a little bit first. I've contributed to the NumPy project a couple of years ago, and DyND is a project that I started to create something that's similar to NumPy, but in pure C++, Python bindings, and to be able to experiment a little bit more with array programming ideas and methodologies for implementing a dynamic array library. So what I think of DyND as is dynamic array infrastructure. So it's a library for helping, for doing array programming and also for building systems that want to deal with dynamically typed array data and interoperate with other systems which are speaking the same language. So a lot of native language bindings are very tightly bound, either statically or to very specific memory layouts, but there are common patterns of how like your floating point is laid out, your integers work, arrays, strided arrays are very common across systems, but it's not often easy for these different systems which talk the same language at the core to get the data across to each other at the fringes. So DyND has three pieces of it, three major pieces that are intended to sort of help play that role. Its type system can describe memory in a way that has a little bit of flexibility for the array-oriented nature of it, and also can describe symbolic types that can kind of pattern match against many different memory layouts, like all integer types or things like that. The array object is kind of the container class. It's similar to the NumPy array. It's atomically reference counted, and it kind of has a setup that combines the type with some type-specific metadata that defines the layout details like the strides and stuff. So it kind of abstracts that part away and then holds ownership to the memory buffers. And finally, the callable object is for function calls, and it's what lets you write new functionality, combine existing functionality, and it's intended for things that operate on arrays. So like I mentioned, core in C++, bindings in Python, both of them are intended to feel very natural from the people who are used to those two languages. So let's start with an overview of the major pieces of the DyND callable. So we've got a registry where all the functions that are intended to be published and exposed to the system go. It's got a namespace structure, and we've kind of mirrored the DyND.nd is how things have been in the Python bindings, and that's mirrored inside of DyND's own representation of where its functions go. The callable object represents a single function that you can call. It's got a bunch of pieces inside of it that hold the information about does it take the input types, figure out what code to actually run on those particular input types. And then to execute the functions, we actually instantiate that down to a lower level resolution or a lower level representation called kernels. And they're basically function pointers plus associated data. And they're structured as contiguous memory, which means that if you have kernels calling each other, when one calls the next one, they're kind of all calling each other and accessing their local data in one contiguous chunk. So sort of going through levels of these kernels should be very cache friendly. So the final thing is functional operations, which take callables, transform them into new things. Like, so broadcasting can be framed as taking a scalar operation and then applying element-wise logic to all the dimensions and then repeatedly calling that scalar function. So let's walk through some of these bits in a bit more detail. The callable has a signature, which basically says what it specifically matches against. And this is written in data shape. So a scalar function will have like just scalar types in it. A matrix multiply, you'll see we have like names matching up. So there are type variables in the system that correspond, and then as we match the input arrays, it will confirm that the dimensions match up just via the type resolution. And then for broadcasting in the ufunc style, there's a type variable that with a ... that means like broadcast these all together. So we've separated out positional arguments from keyword arguments in a slightly different way than Python. So our positional arguments are just for arrays. And what that means is when the kernel gets called, it's just getting the memory addresses of those positional array arguments. And it's intended that a kernel could be called again and again and again on many different addresses from the array argument. So that contrasts with the keyword arguments, which are dynamic, and they actually get to participate in the stages of type resolution and figuring out what code to call. So if you have a keyword argument that says like use this method or that method for your integration of your function, that gets to specialize the code that goes in the end. But if you have something in the positional arguments, that's intended to be like, that's what you kind of compile down or specialize as much as possible to the layout and the type and everything to get that part fast and operating repeatedly on things efficiently. So the basic life cycle of a function, we do signature matching. That kind of just goes through all the arguments, checks them. Type resolution is sort of the main crux of where the magic happens to like pick your specialized code. And it's doing two things. It's lowering to a call graph that we build up for that nested kernel calling and determines the final concrete array type. So after type resolution is called, then DyND can now allocate the output type and then call the kernel giving the output addresses and the input raw addresses to it. So the type resolution is also where if you have a nested structure in your callable, you're going to be nesting down and instantiating multiple of these together. So kernel instantiation just takes that call graph that was created and then writes it out into the contiguous memory that's function pointers and data. And then it's basically just a C function pointer that with a very simple prototype that you just call with the raw pointers. So signature matching is the first step. And these arguments will either be concrete or they can be symbolic. So concrete types will just match exactly. It's like accept or reject. If you have a symbolic pattern, you might say like an array of 64-bit floats. Well, that's a symbolic pattern because the n is a type variable and will like match against any sized dimension type there. And you can say, oh, I want a square matrix just by n times float 64. So when it executes, it's going to, or when it's finished matching, it substitutes that back into the return type, and that will often get you a concrete type at the end. So that's then passed to type resolution, which is an arbitrary function. It takes a whole bunch of data. So it takes those positional argument types, and you'll see it doesn't have access to the data that's there because it's intended. It might be repeatedly, you might repeatedly call this kernel on like 100 million elements. But there's the keyword values, it just gets as is. And then it gets the dictionary that was produced during the type matching. So if it's like, wants to do some special logic about T or S or what the dims were, it has the opportunity to do that. And it gets the substituted type result. And in this example, I made it so that it's still symbolic. That n didn't get substituted because it never appeared on the argument types. And that's okay. That is how we have an opportunity to take the keyword argument values and substitute more in or be flexible about what we do. So resolve gives our final type and our call graph entry. So that's not going to be what we want to do most of the time because another goal of DyND is that it be dynamically pluggable at runtime. So we want to be able to add new overloads or something to a given function. Like let's say you create a new float type. You want to be able to add your overloads to like all the standard functions and have it work. So something like multi-dispatch is a much more flexible mechanism to do that. And multi-dispatch will work in a vast majority of the cases that we produce. So it's also familiar. A lot of languages use it. And it's based on that symbolic type matching. So in this example, we've got these 3 different arguments. They match. So it's basically the most specific thing which will match. So the 3.5 example, it matches the int32 and 32, but it also matches the TT. But that's strictly more general. It's a bigger set of possible matches. So you go with the more specific one. Basically, to do multi-dispatch, you need partial ordering on your signatures, and we get that from a subset relation on the sets of types that a pattern data shape will match against. So this graph is just like showing an example of how such a partial ordering will look. So all of the concrete signatures are completely independent. They're not greater or less than each other, but then the symbolic types kind of have this matching relationship. So there is something this misses that is pretty typical in multi-dispatch, which is implicit conversions, where you like say pass in 32-bit floats, it gets converted to 64-bit float automatically, and it just works. Which I think universal rules for that aren't perfectly obvious because in some cases you might not want that to happen. Like frexp is a C function which splits up a floating point number. It doesn't really make sense to pass integers or a bool to that and have it automatically give you what's the exponent of your bool. It's so it might be nice if it refused to accept those. It's not. We haven't like fully nailed exactly what that's going to be like though. So that's still maybe a bit work in progress. One idea is that we have it be fully explicit as we showed, and then use the sort of kind or categories of types like real or number, and then let you say like, oh, all floating points should match against this signature, and like bake in some conversion codes for those. So that all the exact matches would go to those exact matches, and if it doesn't quite fit, it goes to that sort of more generic signature. And then there's no ambiguity about, and there's no like, which ones should convert. It's explicitly specified when you create the callable. We'll see though. So kernels are the next level down. That's what it gets down instantiated into. That's what actually gets executed. And kernels are all about bundling the code and the data. So calling a C function pointer directly is generally a fast operation. And by bundling the data right beside the function pointer and everything, I think this execution can be about as fast as like a dynamic thing that you call repeatedly could be. Except it has one kind of extension, which is when you instantiate down to a kernel, you can choose. Do you want to just call it once on various addresses all over the place, or do you want to call it on a strided array and have it run on a whole bunch of things at once? So that instantiation level thing allows you to do that, and the kind of cases you might want to do things differently for is like, let's say you want to broadcast an operation across every element of a dictionary. Like those might be scattered around memory all over the place. So you want to do the single, so you don't have to pay the overhead of like checking the count at, oh, it's 1, we go through this case again and again and again. So like cut out that overhead and do the minimal thing for like arbitrary jumping around memory. But if you have an array that's just like simple strided contiguous memory or something, you just want to give it one thing, give it a stride, and have the inner loop just go through it, do SIMD, whatever it can. So this kind of gives you both opportunities. So here's an example of how that might look. The callable got reduced into that call graph. Then we instantiated, and now they're sitting contiguously in memory. And kernel 1 will know the offsets from it to the kernel 2 and kernel 3 to be able to call down to them for individual subcomponents of the elements it's working on. For example, this might be some kind of an add operation which is generalized to tuples, and say kernel 2 and kernel 3 are the add operations for the first entry, which is int, and the second entry, which is float. And then kernel 1 will add the two things separately, like that kind of dynamic composition of the operations is what this is for. So the element-wise broadcasting is one of the key pieces of how this machinery works. So I'll do a little bit of an example that goes into some more detail on it. We start with a scalar callable f, simple signature. We get a broadcasting callable where now we've added these dims broadcasting type variables onto everything. And then the L-wise callable is responsible for handling all the dimension logic and instantiating the scalar kernel at the bottom, so that basically that broadcasting logic gets baked into the kernel structure, and at the end we get natural broadcasting execution. So here's that signature. Let's say we have these two positional arguments as our parameters. We get a call graph that is the broadcast, another broadcast, and then the scalar function. And then we instantiate it, and we get 3 kernels again, where the first one does a broadcast along the first dimension. It's going to be walking along the outermost strides. The next one will be walking along the next set of strides. and the inner one will be doing, well, whatever black box that is. And you'll see I said the top one is single. That's like, we're going to call this once on the array we're operating on. And that's going to call the strided version of the next one down, and then it's going to call the strided one of the innermost one. So we're kind of pushing that inner loop down one. So here's a couple of these functional transforms we support. So reduction, doing something on every neighborhood of an array, or doing rolling window operations. So another topic that's, I think, very important for like specifically Python and dynamic kinds of things is JIT compilation. So the way that this is structured is JITs can both consume and produce these callables. The JIT will need to be plugged into that type resolution system. So it can take its input types, translate those to DyND types, call the type resolution, get the result type, and then hook that in with the C function call in there. And vice versa. It's all defined in a way that the JIT can produce the type resolution and everything based on how its internal logic is. So that isn't quite satisfying 100% for people writing JITs, because it's like, well, you want to take that kernel and inline it and let the compiler like do whatever it can to optimize everything that it can see. And so we plan to eventually add the ability to like instantiate down to LLVM, bitcode, or things like that. Another idea is like balancing between low overhead and high throughput execution. So JIT compilation is terrible if you just have like a few elements. So you really want to do like that piecing together functions if you can in those cases. So choosing between them would be a good thing. So finally, a little bit about integration between these callables and the host system. So we've chosen two languages, C++ and Python, which have very different behaviors. C++ is static. You kind of have to know all the type information ahead of time. Python is dynamic. It's like your types could be anything when they flow in. I also like the idea, or the kind of system where you have node graphs that represent your computations, and people who are not like programmers and are even scared of something like Python can like write little programs and actually get work done without really being programming. So the callable registry is kind of the base level of that. So you can imagine we can set up a two-way relationship between the callable registry and Python modules and submodules. In C++, it's not quite as natural because C++ expects to know everything at compile time about that. So you do a string lookup in the callable registry, and you get a callable, then you can call that. It's going to be fairly slow looking things up by string and a little bit annoying. So we've got ideas for how we might add fast pass when, you know, like sign is always going to support the float type. So why not have a short circuit where we kind of pre-process the sign function and let you get there quicker. Then calling callables is another somewhat tricky thing in different languages, because we've chosen a particular calling convention. Like we've got these positional array arguments and keyword dynamic arguments. It actually matches fairly well with Python, but it is more specific. So we just map, like because Python is so flexible in what it accepts, it's like we map the keywords and positional arguments in a natural way, and that's fine. In C++, well, there's no keyword argument, so you have to emulate that somehow. And you can see that at the last syntax. That's using the relatively new initializer list feature of C++ 11, which lets us get not quite a nice syntax, but something that's pretty compact and is keyword arguments in C++ that are dynamic. So generating callables from these different languages is another thing. So Python, like in NumPy, there's NumPy vectorize, which takes your Python function and then like applies it in a broadcasting way. It's really slow because it's executing everything in the CPython interpreter. I mean, we could do the same thing, but it's like that's not going to get you what you want out of it. So we basically need to integrate with various JIT systems, and we've done some basic JIT integration with Numba. There's more work to be done to like teach Numba about all those details of the type resolution and everything, and have both ways work well. In C++, template metaprogramming works quite well for this. So you can make a one-liner that generates a callable and generates all that boilerplate, and it just uses the some template argument extraction, generates the boilerplate, gives you back a callable object. It's really quite nice. So that brings me to the end. I've kind of gone over what callables are, tried to motivate a little bit of why they're structured the way they are. I mean, the array arguments provide this composability of the kernels. The dynamic arguments provide ways to sort of affect the output type in the ways some NumPy functions like reductions do, and I think we'd like to preserve that style of working. And it supports these both JIT compilation and piecing together like functions and data in a neat way. So that's mostly there. It works quite well, so we're getting pretty close to building out a good DyND standard library. That's it. Thank you. Yeah, so the question is about units in the data types, and have I thought about it? And yes, definitely. I guess, like basically a parameterized type that includes both the unit parameter and the underlying storage type feels like a very natural extension. There's like questions to how that then interacts with other things like composition with arrays, composition with other things. So it's like, can you assign units to a whole array of things, or do you assign the units in the middle, on the inner side? But I think like the basic idea of like a parameterized type within data shape is a good approach for that. One more question? Yeah, there is a getting started. There's a couple of notebooks. The getting started is a little bit more oriented towards introduction to developing DyND itself as opposed to using it. We do have a lot of work to do on documentation that's focused on people who are just going to use DyND as a library as opposed to work within it. But we're if you go to libdynd.org or search for DyND on GitHub, you'll find it.